precious resources by analyzing in 1 month what used to take 10 years.
是谁发明了机械计算机？
Everyday devices translate even the most complex languages from voice into text and images into words.
Xavier is now present.
Helping the visually impaired recognize an old friend, or letting a blind woman read to her child for the first time. Autonomous vehicles give us the freedom to reimagine our city streets and deliver relief to those who need it most, even under the harshest conditions. Robots tap into the power of deep learning to separate trash from treasure and give us amazing new ways to explore other planets. And today, a 2,500-year-old game meets its match as a computer competes with one of the greatest human champions of all time and wins. GPU deep learning is the breakthrough that sparked this AI revolution and fuels your most amazing discoveries yet to come.
Ladies and gentlemen, please welcome NVIDIA co-founder and CEO, Jensen Huang.
Thank you. Welcome to GTC. GTC is about GPU computing, a form of computing we invented 10 years ago. GPU computing has come a long ways. In just the last 10 years, it has enabled amazing new applications, solved problems that weren't possible before, and now it's in the process of completely revolutionizing industries. GPU computing is a specialized form of computing. It solves problems and it can do things that normal forms of computing simply cannot. We've got some pretty exciting things to show you today, so let's get started. Well, GPU computing, this thing that we've been working on for 10 years, is at the beginning of something very, very important. A brand new revolution, what people call the AI revolution. The beginning of the fourth industrial revolution. However you describe it, we think something really, really big is around the corner. About 20 years ago, 25 years ago, 1995, the PC internet revolution started. Several things came together that made the PC internet era really, really exciting. The availability of a microprocessor, the CPU, a standardized operating system, and a standard document exchange system that made it possible for us to share information all over the world. The PC revolution, the PC internet era, has put computers in the hands of 1 billion people. 10 years later, in 2006, two simultaneous things happened. The mobile revolution, the mobile cloud revolution, was started by the iPhone and the Amazon AWS. For some reason, it happened about 10 years after the PC internet era. All of the combined and cumulative amount of innovation that was built into the industry made it possible for us to put computing technology in the hands of nearly 3 billion people and made computing capability available to you wherever you are. From every computer in every home to a computer in every hand. Well, it's 10 years after that. It is now 10 years after that. And we're in the beginning of something very, very big. We call it the AI revolution. In this new era of computing, something pretty amazing happens. Software writes software. Machines learn. And soon, machines will build machines. In this new era of computing, The type of software that's written by the computer is impossible for humans to write, and is therefore able to solve problems that we've never imagined before. In each era of computing, a new computing platform was developed. A new computing platform made it possible for these new capabilities to emerge. The CPU and the standardized operating system called Windows, the ARM low-power SoC, and Android operating system, and the cloud platform made the second era possible, and now the third. A brand new type of processor is necessary to make this type of software development possible. And it put us, put NVIDIA, put GPU computing square in the center of this revolution. It happened in 2012, the Big Bang. The Big Bang of GPU computing or GPU deep learning was 2012. Even though great work had been done in deep learning before that. Even though, in fact, Jürgen Schmidhuber's lab in Swiss AI's laboratory had already started to work with GPUs with deep learning, it wasn't until 2012 that happened. And it's part serendipity, part destiny. The serendipitous part, of course, is that the researchers of the Swiss AI, or in this case, the researchers of NYU, Alex Krizhevsky, under the laboratory of Geoff Hinton, was trying to develop a new type of deep learning network that was incredibly deep. Neural net, as you know, is inspired by the human brain. And it has the ability to learn features from very complicated data by itself. And it does it in the case of deep learning hierarchically, meaning that if you were trying to recognize a human, it might detect edges first from the image. It might detect, after that, small features. It could be eyebrows, eyelashes, pupils, nose, ear. And from that, it learns this is a human head. And from that, it recognizes this is a human. And it has the ability to generalize incredibly well. Generalize meaning that although it learns from just a few examples, those few examples could be thousands of examples, it's able to generalize that all of you are humans. And so the ability to learn features hierarchically and to generalize representation learning was a very powerful idea. It had one enormous handicap. It had one enormous handicap. This idea has been around for several decades, in fact, but the one enormous handicap that it had is it required a large number of examples to learn from. It required an enormous amount of data to learn to write the software. That handicap of being computationally exhausting, that handicap of requiring massive computers for the software to be written so that it could be useful, lasted 2 decades. A handicap that lasted 2 decades, and then one day, because we had caused our GPU to become general purpose, Alex Krizhevsky was able to discover our GPU and developed a deep neural net on that GPU. Serendipity met destiny. And in 2012, he wrote a paper, a milestone paper, and this milestone paper chronicled and described his deep neural network, and he submitted it for a competition. And this young man, who has no experience in, or little experience in computer vision, created a neural net that was able to recognize a large quantity, a large scale amount of images, learning from 1.5 million images, and putting into a contest of recognizing over 100,000 images, it won. This deep neural net that was written by software, learned by itself on GPUs, won the contest. And he beat every computer vision expert and every hand-engineered computer vision algorithm over decades. One young man's paper one neural network called now the famous AlexNet, beat everybody. Unbelievable results. The results of his achievement rang through the industry. I have the benefit of working with companies all over the world and industry leaders and scientists all over the world. The results of that paper, the results of that singular achievement is probably the most exciting moment in computer science that we've experienced in the last 25, 30 years. And the reason for that is the achievement in itself is significant, but the extrapolation of the achievement is daunting. The extrapolation of the achievement, what it means now, what it means to computer science, what it means to computer programming, what it means to the computer industry, what it means to all the problems that we're trying to solve. How is it possible that a piece of software learns by itself and creates such amazing results and beat every human-engineered algorithm that has ever been developed? Well, the stage for the AI revolution has been set. Since then, in just the last 4 years, there's not 1 week that goes by where some deep learning paper has been produced, some lab has new groundbreaking results in deep learning, some company has been founded, some new breakthrough has been achieved. There are 3 very important milestones in the last 4 years that I want to highlight. The first is a collaboration between us and Stanford Research, our NVIDIA Research, and the AI lab of Stanford. Andrew Ng, a world-famous pioneering AI researcher, worked with our laboratory to create essentially a large-scale GPU deep learning system that has the ability to simulate enormously large brains. We can now allow computers to write software for very large problems. And the reason for that, the reason why that's important, is because we want AI not to be a toy. We want it to solve real problems. And real problems are large. And we need large computers that are incredibly scalable so that we can train enormous models. Enormous models. That singular breakthrough, that paper has put GPUs in the hands of literally every serious researcher and every serious software company to solve very serious problems. Big breakthrough in the year 2012, and it turbocharged literally everything. Since then, some other achievements. This is ImageNet. This is the competition that happens every single year, and it was just completed yet again in 2016, and the new winner is deep learning again, based on GPUs. Since 2012, notice first of all the discontinuity in the black dot, the last black dot and the first green dot. The last black dot is human engineered, expert engineered, computer vision algorithm developers. Expert engineered. It was able to achieve 74%, and it stayed around low 70s for quite a long time. In fact, if it wasn't because, and then of course, deep learning came along, AlexNet came along, and we took a big jump. Since then, the models get larger, the architectures of these networks become more complicated, the computational intensity of the networks continues to grow, and one day, last year, we achieved superhuman levels. I am pretty certain not one of us in the audience today has the ability to beat this deep neural net in large-scale image recognition. And it's very, very likely that even all of us getting together, working together as one team, we cannot beat this network in large-scale image recognition. Image recognition using deep neural nets has achieved superhuman levels. It was because of deep learning that has inspired us at NVIDIA to apply this technology to many of the things that I want to talk to you guys about. And in fact, one of the areas that's of great importance is, of course, autonomous vehicles, self-driving cars. It is inconceivable to us, anyways, that we could achieve the level of safety and the level of capability of self-driving cars using traditional computer vision approaches to object detection. And finally, now we have, if you will, Thor's hammer, this incredible magical hammer that fell from the sky to help us solve this great challenge, image recognition at superhuman levels. Just a couple of weeks ago, our friends at Microsoft, XD Huang is Microsoft's speech chief scientist. Speech recognition, as you guys know, is one of the most researched area in artificial intelligence. And the reason for that is because if we can understand speech, we can read, and if we can read and understand language, we can learn. The ability to understand speech will not only change how people interact with computers, it will also change what computers can do. Deep learning has recently made enormous achievements. This is from a paper from XD that he published several years ago. And the work that's done of speech recognition are some of the finest artificial intelligence researchers that we know in the world. Geoff Hinton has made enormous contributions in this area. Deng Li over at Microsoft, XD Huang, of course, and here in Europe, one of the most significant AI researchers, and has made enormous contributions to deep learning use for speech recognition. Jürgen Schmidhuber's laboratory in Switzerland has done amazing pioneering work. They were really, quite frankly, the first to use deep learning with long short-term memory for understanding, to improving speech recognition. Just a few weeks ago, Microsoft announced that after all of these decades, they have achieved quite a significant breakthrough of 6.3% word error rate. Well, speech recognition is really hard. Speech recognition is really hard for some very obvious reasons. For example, vocabulary. The larger the vocabulary, the lower the accuracy, the higher the word error rate. Speech versus spoken versus read speech. You know, when we're talking, we have lots of ahs and ums. Speech is hard because everybody talks in different ways, and there's a whole bunch of, as it turns out, E's. You know, the BCDs, they sound very similar to computers. The EVPs, you know, the PVZs, a whole bunch of E's. So the English language, as it turns out, is relatively hard for computers to understand. It's fairly hard for us to understand. And so speech recognition is something of great difficulty, not to mention surrounding environments where you're inside a car, inside a bar, inside a train station, inside a pub here in Amsterdam where everybody's talking. And so all kinds of different environments creates enormous complexities for speech recognition. We now have achieved 6.3%. By the way, humans don't achieve 0%, and that suggests that these computers with deep learning has achieved quite significant levels of capabilities. Well, these three achievements I highlighted for a particular reason. We now have the ability to simulate very large brains. We now have the ability to recognize images, that is, computer sight. And we now have the ability to recognize speech, that is, a computer's ability to understand what we say. Sight and sound, and the ability to learn. The ability to perceive and the ability to learn is the foundations of artificial intelligence. That is the reason why the world has become so excited about AI. We now have the three pillars necessary to solve very large-scale artificial intelligence. Lots of research is happening in this area. And it's really shaped the industry that we know today. And it surely has shaped us. NVIDIA, as you know, is a GPU company. We invented the GPU. And 10 years ago, we invented GPU computing. We are basically in three fields of endeavor. That is unified by one concept. Our three fields of endeavor, first of all, is high-performance computing. We created GPU computing to solve, it's a specialized form of computing, and it solves problems that normal forms of computing can't. If you wanted to simulate weather, if you want to create virtual reality, if you want to simulate the brain, this is a style of computing, a way of computing that has made that possible. Almost every supercomputer in the world, brand new supercomputers in the world, are accelerated. We started that trend. We represent about 70% of the world's high-performance computers that are accelerated. I think that in the future, every single high-performance computer will be accelerated. The second area of endeavor for us, computer graphics. The simulation of virtual reality. The simulation of virtual reality. This is obviously a very exciting area for us. We love computer graphics. It has fueled enormous amounts of innovation and an R&D effort for our company. And in this area of visual computing, this is a little bit like computing human imagination. We take what's in your mind and we translate it to computer graphics so that all can enjoy. And this new field that we found ourselves in and that we have been propelling in the last 6 years, artificial intelligence, or otherwise computing human intelligence. Some people have said that we've become the AI computing company. Whether we're computing human imagination or computing human intelligence, we've become the AI computing company. But I kind of still think that we are the fun computing company. We get to solve all of the world's fun problems. And we're, if you will, the computing of the future company. In fact, most of the work that we are doing is leading to a pretty exciting future. In the movie Iron Man, Tony Stark is interacting with holographic computer graphics floating in front of him. He has Jarvis in the ambient. Jarvis is helping him fetch information. In fact, Jarvis, as you know, is rendering that computer graphics. Jarvis is talking to him, answering questions, collaborating with Tony Stark. And one of my favorite parts was when Tony Stark puts his hands into the Iron Man suit that he was designing and interacting with for the first time. Merging simulation, virtual reality, augmented reality, and of course, powered by artificial intelligence. If you will, that one scene captures what NVIDIA is working on. This is the future that we're trying to create, and we're super excited about it. And as we come to GTC every year, we're going to take giant leaps towards this future. This is a pretty exciting time. I think all of the pieces are starting to come together, and GPU computing is at its core. GPU computing is what GTC is about. And if there's any doubt whatsoever that GPU computing is being more important than ever and becoming more central to one industry after another, this chart would surely change your minds. The number of attendees in GTCs were requested to go to just about every country in the world these days. We are on a world GTC tour, the first time in the history of our company. After 10 years, developers all over the world has asked us to go to literally every single country because GPU computing is now used in every single country. Every GPU computing is touching every single industry. There's not one software company that I know of today that's not using GPU computing, either a little or just a ton. GPU computing is at the core of computing as we know it today. The number of developers has grown tremendously. It has grown 3 times, not in 10 years, it has grown 3 times in 2 years. 3 times in 2 years. I believe that's exponential growth. It's incredible. 120,000 to 400,000. But this one is just shocking. The number of deep learning developers has grown 25 times in 2 years. It's probably doubled since I started traveling. It's absolutely incredible, the number of deep learning developers. And they're touching just about every single industry. And so the question is, why? Why has AI researchers all over the world discovered the GPU? Why has it? Now, I'm not going to offer you a scientific reason for it. This is a little bit of a cartoon reason, but I think it might inspire you. It might give us maybe a little bit of the understanding for why it is that AI researchers all over the world have adopted the GPU. Suppose I were to say, I'm going to ask the audience to think. I would like to now ask you to think. I would like to ask you to think about an iconic image in Europe. I would like you to think about the Eiffel Tower. I think it's a fairly good choice for everybody. Let's think about the Eiffel Tower. Now, it turns out when I ask you to think about the Eiffel Tower, it's very likely that most of you did a mental image of the Eiffel Tower. Your brain performed computer graphics. Your brain performed computer graphics. If I said, think about Ferrari, it is very likely your brain performed computer graphics. Some probably chose the 458. Maybe some chose the 430. Maybe some chose the LaFerrari. Who knows? But it's probably red. Your brain performs computer graphics, and your brain performs computer graphics in color when you think. It's also very likely that our GPUs, because our GPU is designed like a brain. Your brain, as you know, is not one super processor. Your brain is a whole bunch of neurons, billions of neurons, connected by tens of thousands of synapses each. And each one of these neurons don't perform much work. But together, it's able to think. Together, it's able to achieve something that only we can achieve. Something with trillions of dollars of R&D the computer industry has not yet accomplished. The GPU is maybe a little bit like a brain. We have a whole bunch of processors, thousands of processors that are working in parallel to solve a problem. Thousands and thousands of processors. In the case of a supercomputer, the largest supercomputer in the United States is powered by NVIDIA Tesla, and it has 16 or so, almost 18,000 processors. GPUs. Those GPUs have thousands of processors inside. Altogether, about 36 million processors are working together to solve a problem. Our GPU computing approach is a little bit like a brain. And so maybe those two reasons inspires us, give us some evidence of why it is that researchers all over the world has jumped onto GPU computing as the fundamental processing approach for AI advancement. Well, GPU deep learning is a new computing model. Now, before I go off and tell you about the products that we're going to announce today, and the new initiatives and our new partners, let me first describe why this new approach is different. Whereas computing in the past is engineers sitting in front of computers using Visual C++, developing essentially recipes, incredibly complicated recipes that are followed step by step by step. And they're written by engineers. And what the engineers wrote is what it does. What the engineers wrote is what it does. What was written is what it does. And when you're done, you compile it, you test it to make sure that it performs according to your expectations, and then you release it to the world for functionality, for application. Software engineers write the software, QA engineers test the software, and we release the software into production, and the software does exactly what we expect, what we wrote it to do. If there's a bug, we eventually find it, we fix it. We fix it, we test it, we release it. We find a bug, we fix it, back into that loop. GPU deep learning is a little bit different. There are several different elements of GPU deep learning. The first part is training. It's about this deep neural net learning from an enormous amount of data. It's learning from digital experience, which is what data is. Because the world has an abundance of data today, we have an abundance amount of experience to train these neural net with. This is a computationally intensive part of deep learning. Incredible. And I'll illustrate some in a second. The output of that is a deep neural net. And then you infer. You now apply that network to infer, and then you have intelligent devices. Now let me go around this loop one more time. So in the case of training, we have billions of trillions of operations. Billions of trillions of operations. Billions of trillions of operations. That's a fairly large number. And that's one of the reasons why it takes so long to train a network. But what you have done is you train large models, and your goal is to accelerate your time to market. You've created a network. This network is a neural net with hundreds of what is called hidden layers, meaning layers on layers on layers on layers. And as a result, we can generalize, we can learn and generalize representations that are based on hierarchies of features. That there could be edges, eyebrows, eyes, head, body, human. That all of this data underneath could eventually be abstracted and be represented with a vector, a piece of information that says human. Lots and lots of raw data, human. The ultimate form of compression. Lots and lots of images, output, feature, representation, human. Amazing, amazing result. Our brain has the ability to do that, to take raw information and somehow extract it from it the essential pieces of data, the essential nuances, so that we can abstract that data into a higher level representation called human. We put that network in data centers all over the world. These are data centers that are populating all over the world, hyperscale data centers. So every time you make a query, you say, find human, image of a human. It is very, very likely, well, it's certainty now, that it goes through an artificial intelligence network and it searches its entire library of images, and it detects, finds the images that best represent your query, says human. When you do a voice query, a voice command, OK Google, it goes through the same similar type of process. It goes into the network, and the network infers from you what you need to do. This is going to be a huge market, and the reason for that is this. Almost every single query in the future is going to be AI-based. Every single time you touch your phone, every single time you use the internet, it will be routed through an AI network. Billions and billions of queries. They could be video, they could be voice, they could be music, they could be text. They could be requests for commands. They could be things like, help me book a trip. Help me book a trip to Monaco. GPU inference makes this response time incredibly fast, and as a result of that, it improves the throughput of your data center, i.e. reduces cost. We're going to put these networks on devices as well. This is the era of the intelligent device. Your vacuum cleaner is already relatively intelligent. It has the ability to be much more intelligent. Your toaster, your coffee maker, your house, the cameras that watch the outside of your house, a little microphone that's connected to a speaker, otherwise known as Amazon Echo. These devices are going to be infused with artificial intelligence so that they can be much, much more intelligent. Deep learning and AI is the fuel, it's the technology for IoT. This is going to be pretty exciting. Well, so what we just went around is basically how GPU deep learning works. It's this new model of computing, and notice very little coding, a lot of computation. Very little coding, an enormous amount of computation. Very little coding, an enormous amount of computation. And the amount of computation is going to grow. I'm showing you 3 pieces of work from 3 very important AI research organizations in the world. The first one is Google. This is Jeff Dean's, it comes out right out of Jeff Dean's PowerPoint slides, and he basically says the important property of neural net. The important property of neural net is that the results get better when there's more data, when they're bigger models, i.e. bigger brains, and as a result, you need more computation. A bigger brain with more experience, lots and lots of opportunity to learn it with computation, makes it for better results, higher quality network. Second, I'm showing you here Microsoft's progress in their image recognition network. This is AlexNet, and it's just tiny by today's standards. It's just tiny by today's standards, only 4 years old. It's 8 layers. It performs 1.4 billion operations, okay? And it achieved an error rate of 16%. And literally 3 years later, Microsoft announced the ResNet, the deep neural net, super deep network, 152 layers. And recently, SenseTime announced that they broke this record with a network that is 4 times deeper. Several hundred layers deep neural network. These networks are getting larger and larger and larger. And as they get larger, they can recognize more and more and more subtle details. As a result of that, their accuracy goes up. Baidu's Deep Speech 1 and Deep Speech 2 went from 80 gigaflops of total processing to train that network to something that was 10 times larger. Unbelievable advances and computational demands in deep learning. As you can see, these numbers are far, 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 far higher than Moore's Law. And that is the handicap of deep learning at some level. This new computing approach, if it were to advance, needs the conviction of an industry, or at least the conviction of a company, to push computing technology at a pace that is so much greater than Moore's Law. Well, we thought, why not us? We think deep learning is amazing. It is this incredible hammer that fell from the sky. It has the ability to turbocharge AI. It could be the foundation of the next generation of computing. And it can solve problems that we only dreamt of solving our whole lives. And for me personally, I want to do it before I get to retire. And so I've been doing my job for almost 25 years. And I want to dedicate my next 40 years to this endeavor. And so I better get going. Well, we invented this. We decided, after we started to understand about deep learning, that in fact, the rate of change has to grow, not diminish. We recently rolled out Pascal. And the thing that was incredible was this. The first customer of Pascal, the first customer of this incredible new processor, that is 65 times the performance of what we were able to achieve 4 years ago. 65 times. I mean, it's kind of, I love every GPU we've ever built. You know, a parent has to love every child. But what is that about? That is the picture of underachievement. And yet Kepler, this GPU, was the GPU that Alex found. This was the GPU that accelerated deep learning by a factor of 40 over the CPU. And look at it. A picture of underachievement. A picture of underachievement. So, Kepler to Maxwell to Pascal, you could see we are incredibly serious about the advancement of this field. The first customer DGX-1 is an open laboratory called OpenAI. And their mission is to democratize, to advance this field, and it has gathered some of the world's finest researchers in AI. To democratize this technology, it's an open industry laboratory, and they were the first email that I received as soon as I announced this product. By the time I walked off stage, they've asked with a great deal of urgency, they need a machine like this to advance their science. So NVIDIA's DGX-1 is the system that embodies the Pascal processor that is 65 times faster than what we were able to achieve just 4 years ago. Well, the thing that's really great is that our platform is so accessible. You could get it in a gaming PC, you can get it in a laptop, you can get it in a server, you can get it in a supercomputer, you can get it in clouds, you can get it in DGX-1s. You could build it yourself, you could buy it, you could rent it. You could get NVIDIA's GPU computing platform literally every country, everywhere. As a result, every single framework that is being developed for AI has been optimized for the NVIDIA GPU platform. If you are an AI researcher, this is your platform. And we're committed to continue to advance it at a rate that is incomparable to the rate of computing advance, frankly, in the last 30 years. All of the curves that we have seen and the progress of Moore's Law has to be broken. We can't slow down. We've got to hypercharge it. This is our first example of hypercharging Moore's Law. Well, to bring this capability to the world, we need a whole lot of partners as well. And I'm super, super pleased and super proud to announce that IBM is a great partner of ours in this new area of AI computing. As you guys have heard IBM talk about, cognitive computing is the future of their company. Cognitive computing has the ability to solve some very, very large problems. And underneath that cognitive computing services stack called Watson needs to be a supercomputer. And that supercomputer needs to have super capabilities for artificial intelligence. We've been working with the IBM team. It was announced, I guess, a couple of years ago. We worked together to create a technology called NVLink. The Power 8, which is the fastest microprocessor in the world today, is connected to our GPUs directly through the fastest single interconnect that humanity has ever created. Between Power 8 and the NVIDIA Tesla GPU is this interconnect called NVLink. When you connect all of them together, you have this network of fast processors, fast CPUs and fast GPUs, and it can be dedicated to solve AI problems. Partnership with IBM. Well, today we're really excited to announce a new partner. I'm going to show you some amazing applications of AI and some amazing applications of GPU deep learning. And the breadth and the reach of our platform in just about every industry. But there's one area of research that is of great importance to us. And I think this is an area that we can really move the needle for society. And it's in applying AI for the work of companies all over the world. To apply AI for the work of companies all over the world. And today we're announcing that SAP and ourselves are working together to make the world's largest, one of the world's largest enterprise software companies, to integrate it with the NVIDIA DGX-1 and our GPU deep learning platform so that we can bring AI capability to enterprises all over the world. We're partnering with our Germany and Israel team. Amazing team working on this now. And when we're successful, hundreds of thousands of customers of SAP will have the benefit of AI computing. so that they can turbocharge their business. Really exciting. Let's give a round of applause to SAP, please. DGX-1 is an instrument of AI. Just like the Large Hadron Collider is an instrument of particle physics. Without that scientific instrument, you can't do reasonable particle physics advance. The R&D budget of DGX-1 was $2 billion. This is the most expensive, most ambitious modern computing endeavor in recent history. 10,000 engineering man-years went into it. We're now shipping DGX-1. This incredible and this important instrument of AI research should be put into the hands of the world's best AI scientists. We put it in the hands of OpenAI, the laboratory at Stanford, Peter Abeel's laboratory at Berkeley, Yoshua Bengio's laboratory in Toronto, or Montreal, excuse me, Yann LeCun's laboratory in NYU. All of the world's most important AI laboratories must have access to the most capable instrument of AI research that the world has ever known, DGX-1. And so today we're super proud, super excited to announce that the German Research Center for Artificial Intelligence and the Swiss AI Lab, where Jürgen's located, will be the two designated research centers of the NVIDIA AI Lab here in Europe. They'll have access to our DGX-1 supercomputer. They'll have access to our resources so that we can advance important areas of research in AI that otherwise wouldn't move along as fast. And of course, we have all kinds of abilities to collaborate to move AI into society in a good way. Okay, so let's recognize these two research centers here in Europe. They are truly pioneers in AI, and I'm so delighted to partner with them. Thank you very much. So, AI training, GPU deep learning training. Now let's talk about data center inferencing. This is a massive market. You train the software, you train the network so that this network could be as great as possible. You train it with an enormous amount of data. It takes billions of trillions of operations. It takes months and months and months. This is what researchers now do in the software development cycle of their new services and new software. When the network is complete, or it's ready to be tried or ready to be enjoyed, you put it into a large-scale, hyperscale data center. There are millions, tens of millions of servers in the world today that support cloud computing and all of the internet services that we enjoy. Tens of millions of nodes of hyperscale data centers. This is a brand new market for us. And now that these networks are trained, they're ready to be deployed into production. And if we were to design the exactly right accelerator, the exactly right GPU, we can make it possible for these networks to be inferenced, meaning when you ask it a question, what is this image? What is this song? What did I say? When you ask it of a query, that it would respond instantaneously. And when billions of us were to make queries simultaneously, and some of the queries are extraordinary queries, when we're able to make these queries and have it respond instantaneously, and for these data centers to be able to support literally 1 million times more workload without having data center costs go up by 1 million times and energy consumption to go up by 1 million times, we need a special and new accelerator. We call it the Tesla P4 and P40. They're two brand new accelerators. One of them is for our large-scale processing, but the second one, the P4, is designed, thank you very much. So this is designed for GPU servers. So this is designed for GPU servers. And this cute little thing, if you can ever call a GPU cute, is the cutest GPU that has ever been invented. The Mercedes S600, the Mini Cooper. This little thing, P4, fits into a OpenCP hyperscale server that's 1U. It consumes anywhere, depending on your configuration, whether you want it to be 50 watts or 75 watts. The thing that's really amazing is this. You have 50 watts here, you have 250 watts here. This is 40 times faster than the fastest CPU at AI computing, at GPU, at deep learning. So you plug one of these things in, and you replace 40 nodes. Plug one in, replace 40 nodes. 40 nodes is basically 3 or 4 racks of servers. Replace it with one of these. Incredible amounts more performance, incredible savings. This, you plug it into this little tiny server, and it's 40 times the energy efficiency of a CPU. 40 times. What used to be a 1,000-watt CPU node would be 40 times less. Incredible, okay? So Tesla P4 and Tesla P40. Thank you. 40 times the energy efficiency and 40 times performance. Well, that's just the GPU. We've optimized the GPU. We optimized this new generation of GPUs with new architectures for deep learning and new instruction and new numerical formats that are optimized for deep learning. As a result, we get a huge boost in performance. But on top of that, every new architecture essentially needs this new optimizing compiler. And we're announcing for the very first time a runtime called TensorRT. TensorRT. What TensorRT is a performance optimizing inferencing engine. It's a software that goes along with P40 and P4. And when you put the software on top, when you run the software, and because it supports all these different numerical formats that our GPU support, and it has the ability to smartly fuse operations that are vertically in the network or horizontally across a layer of the network, eliminating work, fusing operations together so that you could do it in one cycle. And it does a whole bunch of auto-tuning so that the network that you trained on the GPU computing platform is now optimized for runtime on our GPU computing platform. We already support VGG, GoogleNet, ResNet, AlexNet, and these networks and all of the custom layers that you guys want to do in between. We're going to support in the future, of course, all the networks. Okay? So TensorRT, really, really, really important innovation. I'm super excited about it. Congratulate the engineers that worked on this. It's available today. Go to our website to download it. Well, let's take a look at all of this. So what I'm going to show you is this. Imagine you are a hyperscale data center and you've got videos that are streaming, that are being loaded up. And you know that live video today is one of the most frequently shared forms of social content. And the thing about live video is it's not recorded. And so if you don't enjoy it, it's gone. And if there's live video that you would like to share with your friends, it would be nice if as you're uploading the live video, it already knows which one of your friends or which one of your family members or your relatives would want to enjoy that live video. And so what we need to do is to make it possible for the data center to literally look at every single live video stream that's going by. Every single mobile user, everybody who's loading live video in the future, and we're going to be loading a lot of live video in the future, every single one of those videos, every single moment of it, we were going to apply artificial intelligence to figure out, is there something of importance in here? What is being shown, and who would be interested in seeing it? What is being shown and who'd be interested in seeing it? So why don't we do this? 90 videos are streaming into our server, into one node of our server. Edward? Yeah, let's go ahead and run the video first. Let's show people, this is the video, for example. One stream at a time. There are 90 different streams. They're all running at 720p. And you're up, we're loading these, for example, into YouTube Live. It could be Facebook Live. It could be Periscope. And these are all live videos. And what we need to do is number one, is we need to figure out what is it that we're looking at. Now, for all of us, we probably can tell what we're looking at. That's probably somebody doing push-ups. Okay? That's probably somebody playing a guitar. That's probably two people making dinner. And this is somebody playing a formidable ping pong opponent. It just always seems to come back. Okay? So let's go ahead. Can you go ahead and label it? Let's go figure out what the computer sees. So the computer thinks that we're playing table tennis, that this is sumo wrestling, that there's somebody on a swing, that they're rope climbing, that they're rowing, and Tai Chi. So the computer was able to learn from looking at all the videos that it was taught with, and now when we load new videos into it, it's able to recognize it. And suppose I had a service and I said, look, you know what, I'm only interested in people playing music. And so it's got to be smart enough to recognize that these are people playing music. What if it's people playing sports, for example? Okay, so it would recognize people playing sports. And suppose I just wanted water sports. Okay, and so the amazing thing is this. In the future, as we stream video, artificial intelligence network that's able to recognize images, and artificial intelligence networks that can recognize the meaning of the image, what is known as semantics, what is the context. By understanding the meaning of the image, we can now have more information by which we can filter, search, or to recommend to people. This is something that's kind of cool. So the next thing that I want to show you, thank you, Edward, that was great. How could you teach? So we can teach a neural network how to recognize things. We could teach a neural network how to recognize things. But how do we teach something that we've always thought is the domain of humans, which is creativity, artistic capability, something that defines what a human is, okay? And so is it possible for us to teach a neural network artistic capability, artistic flair? And so what we did is this. We took a whole bunch of videos, a whole bunch of different arts by different artists, for example, Picasso and others. And we trained a network to recognize the style of Picasso, or recognize the style of a traditional pencil artist in Asia. We teach them these styles. And then what we're going to do is we're going to show it an image, in this case, an image, this is where am I? This is London, right? The flag of London, is it? Yeah, flag of London. And so this is London, and we show it an image, and it would repaint it. Not filter it, but repaint it. We take this image, and we say, paint it again with a different style, with the artistic style. It could be Monet, it could be Picasso, it could be Van Gogh, okay? And so take an image and repaint it. And suppose we could do it so fast. Suppose we could do it so fast with our GPUs, we could do it on live video. And so let's take a look at some examples. So let's first show some videos. So these are some beautiful places in Europe. Okay, so we have some live video footage. We recognize that. Suppose, let's take these live videos, and now let's redraw it with an artistic sensibility. For every single frame, this neural network, this artificial intelligence network, will redraw it. Let's go ahead. It's not a filter. I guess it could be a filter. You can think of it as a filter. But we're redrawing every single frame. Every single frame is being redrawn. one frame at a time. Isn't that beautiful? This is what Picasso would have done to a movie. Incredible. A neural net artist repainting all these different frames, turning it into video. We've now seen all kinds of interesting neural networks. We know that we could take the arts of certain styles or certain time frame, and we can learn it into a neural network, and that neural network can actually generate new art, completely generate new art, and images that looks like it was done by the artist, but has never been painted before. Okay, this is one example doing it in real time. Thank you very much, Edward. What you were looking at was the Tesla P40 with a network that was trained with everything I was describing, this new artistic flair, trained to be an artist. Video was coming in, and it was regenerating the video into this new art form. Okay? And then previously, you were looking at a large number of streams, 90 different streams of video, and we're recognizing what's in the video, the semantics of the video, what's happening, not just there's a person, but the semantic, what they're actually doing. And we're labeling, we're detecting those videos based on those semantics. Well, the applications for deep learning, GPU deep learning, is really broad. And the reach in the last several years of our GPU deep learning platform is really quite daunting and quite amazing. And I'm just, the reach and the new services that are being used on our GPUs are growing every day. In fact, if you look at Jeff Dean's presentation at Google, just literally 3 years ago, they have some 20 different applications internally at Google that was using deep learning. It has now grown to nearly 3,000. That's an exponential growth in just a couple, 2-3 years. Facebook talks about deep learning literally all the time. We have great partnerships with Baidu. Yelp uses deep learning for recommendation and recognizing which one of the images are best to show their customers. Microsoft uses deep learning for Cortana, uses deep learning for their speech recognition. Netflix uses deep learning for movie recommendations. The list goes on. The list goes on. Pinterest uses deep learning so that you can now take an image that you like and you want to know where to buy it. And so it recognizes what's inside that image, and it recommends things that you can buy that are similar. Not the same necessarily, because you might not be able to buy that, but similar, and points you to those websites. The number of AI-powered, GPU deep learning-powered consumer services is literally everywhere in the world. I frankly don't know of one yet, one consumer services that doesn't rely on it. NVIDIA's GPU, our platform, is also available on services. It's available on Alibaba, it's available on Amazon, it's available on Microsoft Cloud, it's available on IBM Cloud. If you're an enterprise customer, we have enterprise partners who configure servers that are ready for deep learning, GPU deep learning. And so it could be Dell, it could be HP, it could be IBM, it could be Cisco, it could be Lenovo. We are able to literally reach every corner of the world with GPU servers designed and configured for deep learning. And now with the partnership of SAP, we will soon have applications that are running on these servers to serve the world's largest enterprises. If you want to build your deep learning supercomputer and have a special need or special configurations you would like to build, we also have ODM partners, GPU server makers, GPU server builders in Taiwan and all over the world that could have them ready for you. Tens and tens of configurations, just about every single version, from 1U to 2U to 3U to 4U, from 1 to 2 to 4 to 8 GPUs, whatever configuration size you would like to have, every single version of our GPUs are all supported. And so as you can see, whether it's services that uses NVIDIA GPUs to cloud services that rents the platform to you, to server companies that can offer you servers designed and optimized for GPU deep learning, to ODMs and server builders that can help you build it. However you would like to have it, NVIDIA's GPU deep learning platform is available to you. That is one of the most important works that we've done in the last several years, so that we can put this platform, democratize it, and make it available to literally everybody. Well, as a result, startups are cropping up all over the world. We now know of 1,500 startups around the world that are deep learning-based startup companies. They use deep learning to solve some very important problems. In the case of Deep Instinct, they're using it for cybersecurity. If we can recognize very, very subtle differences in how somebody were to rummage through our files, that subtle differences would be an intrusion. And so they can use AI and use deep learning to identify the subtlest of differences and subtlest of intrusion patterns. Deep learning for genomics. If we can read and understand the human genome, and we can do it fast enough, we have 20,000 in our body. But that's not the hard part. The hard part is, first of all, understand what those 20,000 are, and then as they mutate, to get in front of it before it spreads so that we can get ahead of it. Deep learning for self-driving cars, a really tough problem, and we're going to come back to that. Deep learning for advertising. This company, Nerve, has the ability to recognize a logo, a brand, a trademark in live video. And they could literally, in a fraction of a second, recognize it for an hour of movies in a large-scale GPU server. So as a result, they can show the advertisers all of the places where their brand has been exposed and their brand has been presented to customers. Great for companies who are advertising companies. AI startups here in Europe, some really amazing stories. Benevolent AI. There are 30 million medical stories, medical papers in the world. Every 30 seconds, a new medical breakthrough is happening, and a new medical paper is being published. Every 30 seconds. Now, I don't know how much time doctors have to spend in reading papers, but it's just impossible to stay on top of the torrent of new breakthrough medical research and the papers that are being written. There are over 100 million chemical compounds that our bodies react to positively or otherwise. There are tens of millions of patients of various forms of disease. They would like to use deep learning to sort through, rummage through, and to understand, to process all of that unstructured data to discover insights, to advise doctors on how best to discover and how best to invent the next cure, the next drug. Well, they were using an Amazon cloud service to process all of that data, and they estimated that it would have taken way longer than a year to process the data that I just described. And so here in Europe, Benevolent AI is the first customer of DGX-1. With the DGX-1, their researchers can help doctors now process through that enormous volume of data in about a week. From over a year to a week. A year is basically impractical. Nobody's going to use that approach. Nobody's going to use that approach. But now we can, with DGX-1, this instrument of AI, this AI supercomputer, we can now do that processing in basically a week or two. SmileArt has the ability to recognize faces, and they're used in IVA surveillance systems so they can look for people who are lost or look for people who are wanted. Deep learning for facial recognition. What's really special is this. Most of the time when you're looking at faces, it's not like getting a driver's license or a passport photo. It's very unlikely that the person you're trying to find is looking at you like this. It's very likely they're either somehow looking away, They might be occluded. They might be in shadow. Their hair might be down. They might be wearing a hat. They may have aged a little bit, gained a few pounds, okay, got a tan. They might have changed just a little bit. And SmileArt has the ability to recognize that in just a fraction of a second. Intelligent voice, insurance companies, companies that have call centers. It recognizes and it follows everybody's, it basically recognizes the speech of everybody on the phone. And not only that, it detects their emotions. And so that you could figure out a way to understand whether the person who's on the phone with you may be deceiving you, for example, for an insurance claim or a financial trade or something like that. Intelligent voice, really interesting. This one's really cool. Sadako has been trained to recognize, this AI network has been trained to recognize what is plastic versus what's trash. It has, as a result, automatically picked up 60,000 tons of plastic by itself. And now that plastic could be used to be transformed into something else instead of being put into landfill. Sadako. Really, really exciting. And of course, that work is something that is very complicated, as you can imagine, because all the objects that are coming through are all very different. Inferencing in data centers. Pascal, P40 and P4, TensorRT, data centers all over the world, brand new market for us. Now that these networks are being developed and they're ready for production, we can now put it on these servers and put it into the hands of customers all over the world, service providers, startups all over the world. I want to talk about intelligent devices, what some people call IoT. But if we infuse it with artificial intelligence, these devices can be rather interesting and be used to solve all kinds of interesting problems. You know, whereas the PC era introduced computers to 1 billion people, and then mobile cloud introduced computers to 3 billion people, I believe the AI era would put tens of billions of intelligent devices connected to the internet. And these devices and these machines, these autonomous machines, could be of all kinds of interesting sizes and shapes. Only our imagination limits us. Whether it's a camera that only records when something interesting is happening, or a little tiny camera and display and microphone and speaker is a little tiny agent called Jibo. And it's just talking to you. And it knows who you are. It might tell you a story. It might turn into a video conferencing system, like Call Mom. Tell you what the weather is like today. It might be something like Echo. Essentially an artificial intelligence network connected also to an artificial intelligent cloud. It might be a drone that's completely autopiloted. And it flies around looking for people to save or delivering drugs, medicine to somebody who's in harm. It could be something as simple as a grocery delivery robot that delivers groceries to you from around the neighborhood or delivers pizza. These internet-connected artificial intelligent machines are going to start cropping up. And what they need is an AI supercomputer. They need a computer that's battery powered. They need a computer that has the capability of AI and has the ability to be instantaneously responding to the circumstances around it. And so we created this embedded AI supercomputer called the Jetson TX1, running TensorRT, the network that we were talking about, the inferencing, optimizing software that I talked about earlier. This little tiny computer has the ability to recognize images and sound and learn and do amazing and wonderful things. Little tiny AI supercomputer. Well, having the system is one thing, but one of the greatest challenges right now is, what does AI computing mean to software developers? And how do software developers take advantage of this amazing capability called deep learning? And so we've created the platform for it. If you come to NVIDIA.com, our SDK is rich rich with all kinds of software and algorithms for your AI supercomputers. But something that we're doing that I'm super excited about is we're starting an institute to teach applied deep learning. How do you take the problems that you would like to solve? And what kind of tools do you have available to you? And how do you use those tools to create essentially an embedded system or a service that you can deploy this network into in a really optimized way? We call that the NVIDIA Deep Learning Institute. And people are so excited about it. I think there's, today, I think there's 300 people who are going to be attending it. This Deep Learning Institute that we've rolled out has been offered all over the United States. It's been offered in Japan, it's been offered in China, it's been offered in Taiwan, and it's sold out every single time. And so as a result, we decided to partner with 3 very large and incredibly successful digital education platforms, Coursera, Microsoft, and Udacity. So we're super excited to partner with them. And we'd like to spread this new way of doing computing all over the world. We want to democratize deep learning. We want to democratize AI computing. So NVIDIA Embedded AI Computing Platform. I want to talk about something that's really, really important. And this industry is not only large, the problems, the challenge, the technical challenge of creating autonomous vehicles and to bring AI to this industry is not only extraordinary in technical challenge, but it's also extraordinary in society benefits. Fewer accidents, more utility for the vehicles that we have, lower cost access to mobility, making mobility accessible to people that otherwise wouldn't have it, and maybe even a complete redesign of how our cities are. AI for transportation is a very, very large industry, and that's one of the reasons why so many people are focused on it. The thing that we've mentioned, we've talked about for some time, and it's becoming more obvious to everybody, is that autonomous vehicles is not about smart sensors only. It needs smart sensors. It needs lots and lots of them. But it is, if you will, a robotics problem. It is an AI computing problem. You have to first, number one, perceive what is happening. So if I were to show you this particular scene and you look at this, the first thing that you have to do is you have to perceive what is happening. What are the things in it and what's happening? The semantics of what's happening here. That there's cones, there's workers, there are cars, it's obviously a construction site. And this construction site wouldn't have been obvious to you if all we did was detected cones and lanes and cars and signs. That this particular scene is different. That somehow a school bus that's driving down the road and a school bus that's parked by the sidewalk is a very different condition that we have to think about it very differently. Number one, perception. We have to perceive the world around us, sense the world around us. Number two, we have to reason. Reasoning is one of the most important things that we do as humans, and that's one of the most important things we have to do as AI computing. We have to reason. And then number three, we have to plan. What do I do now? Well, as it turns out, in this particular case, the plan is not to stop. It's got red all over it. The plan is simply to drive more cautiously, but to drive. Stopping is simply the wrong answer. We're going to create all kinds of congestions. And so let the people work, and we should drive through it. We have to reason, and we have to plan, and we have to drive accordingly. At the foundation of all of this is learning. And that's one of the reasons why deep learning has an opportunity to help us solve all of these challenges that we've been waiting a long time to solve. And that's one of the reasons why NVIDIA has jumped in with both feet to work with the automotive industry to create a scalable platform for self-driving cars so that together as an industry, together we can help revolutionize transportation. Our platform is called Drive PX2. And it came with some amount of questions about why is Drive PX2 this way? Well, it turns out that autonomous vehicles comes in all kinds of sizes and shapes, and it's now becoming clear that, in fact, having a scalable platform with one architecture is really the best way to go. And the reason for that is this. Different car companies, different segments of the industry, different applications, and different countries have a different vision or a different time scale of their vision for autonomous vehicles. It could range all the way from somebody who would like to create an auto cruise, highway cruising capability that is incredibly safe, highway cruising capability. But it's not just about sensing, it's localizing, it's reasoning, it's planning, it's acting, it's AI computing. To somebody who would like to be able to say, take me home, and it actually takes you onto the highway, off the highway, destination to destination, auto chauffeur, obviously require a different amount of computational capability. And then number three, somebody who would like to build a fully autonomous vehicle where there are no drivers. If there are no drivers, you have to be 99.999999% accurate. And the reason for that is because if something happened and the car doesn't know what to do, it stops. It remains stopped for a long time, maybe forever. And so that car, if you have a fleet of these cars, they're eventually going to find something they don't recognize. You're going to have a fleet of cars that are all stopped, just all over the world. And so full autonomy requires even more ability to detect the very corners of conditions. And so all of these platforms are designed so that we can address different segments of the autonomous vehicle spectrum and everybody's different visions. We call it Drive PX2. It allows us to do perception, to do reasoning, to do driving, and it consists of basically three parts. The AI computing part, which is the processors, the computing system. The operating system that takes sensor fusion in, does all of the AI processing, connects it to all the AI algorithms, and do it so fast that the car can actually respond to adverse conditions in time to take the appropriate action. You have to do that fast enough. So performance matters and scalable. Well, today, when we launched Drive PX2, we showed everybody the large version of it because our earliest customers wanted everything. We're working with some 70, 80 different partners around the world, startup companies, taxis as service companies, shuttle companies, trucking companies, branded car companies, mapping companies. This $10 trillion industry is quite large, as you can imagine. This $10 trillion industry is quite large. And there are players, important players in the ecosystem all over. And so we started with the highest performing configuration and at CES. And there are all kinds of people who are using it today. This is the smallest configuration of it. This is Drive PX Cruise. This little tiny computer connects to a couple of front cameras and has the ability to recognize what's in front of you, to localize where you are, to connect with a high-definition map, and to update that high-definition map because it can recognize the surroundings. It could do SLAM, and it could update the high-definition map, and it's nice and small. Fully integrated computer. Okay, so this is the Drive PX2 Cruise. We recently announced that this computer, in order to create an autonomous system, needs to include not just this computer and the algorithms inside, but also connect it all the way to the cloud. The proper autonomous vehicle platform is a cloud-to-car platform. It's a cloud-to-car platform. From HD map all the way down to the AI supercomputer. HD map all the way down to the AI supercomputer and all the software in between. And we announced in China a partnership with Baidu. That Baidu has selected the NVIDIA platform for their mapping cars, for their self-driving vehicles, that would be used for OEMs, as well as their self-driving taxis. This one computing platform will be used in those variety of use cases, and it would be the same architecture, Drive PX2. The operating system is called DriveWorks, and it's connected to the Baidu Cloud. Well, today I'm super excited to announce that we're partnering with one of the world's largest and most pervasive mapping partners, TomTom. That TomTom has selected the NVIDIA Drive PX2 to be incorporated into their mapping cars. And that together we're going to create a cloud-to-car platform for the Western market. TomTom has mapped a very large part of the world, as you know. One of the world's great mapping companies. Their service is used by nearly everybody. And we're going to work on basically three things. As TomTom maps the world, they're collecting video. That video has to be processed and turned into a high-definition map. That processing is enormous. It is the grand challenge of supercomputing, to literally record the world and turn it into an HD map. It is a computational challenge of extraordinary proportions. Recognizing lanes, recognizing objects, recognizing structures, recognizing what is car and don't and reject it, turn the whole thing into a three-dimensional map, register it, fuse it, so that it is coherent, and it has to be within a few centimeters. All of that processing is done in their cloud. The first thing we're going to do is we're going to work with them to accelerate that processing so that it could be absolutely super real time, so that we can collect videos as fast as we want in the future, and we can continuously crunch it and turn it into HD maps. The second thing is the Drive PX2. The Drive PX2 will now be their in-car HD mapping system. Not only will it continuously collect and update differences into the map to be fused with the HD map, and then thirdly, together, we will have a cloud-to-car platform. HD map in the cloud, AI algorithms, localization algorithms, and an AI supercomputer for the car. Ladies and gentlemen, let's welcome Alain Detey, who is the board member of TomTom, the head of HD mapping. Alain, come on up.
Hey, Jack.
Thank you.
Hi. Hey, thanks for organizing the conference here in Amsterdam. It's
Thank you.
literally 50 meters away from the TomTom headquarters. So,
Well, that's exactly where we should do it.
Yeah.
We chose it for that very reason, so that we could announce our partnership. So first of all, I think it would be great if the audience had the ability to appreciate the magnitude of the problem of mapping the world.
Yeah.
I know it sounds nice when people just HD mapping. It's such a short phrase.
Yeah.
But the magnitude of the problem, tell us a little bit about that. How much of the world have you mapped?
Well, at this moment, there's 47.1 million kilometers of roads in our map database. But only 120, well, actually tomorrow on the Paris Motor Show, we will announce a bit more, but can't speak about that. 120,000 kilometers is mapped in HD. So that kind of gives you the perspective.
So 47 million kilometers.
Of which only 100,000 HD.
Has been mapped in HD.
And with that, 120,000.
So you're saying we're almost there?
Yeah. It's a small endeavor.
You're saying we're almost there. Now, out of that, so 47 million, how much of society does that represent?
47.1 million is about 70%.
70% of society, known, developed
world,
society.
Yeah.
And out of that 47 million miles, you've surely driven more than 100,000 miles.
Absolutely, yeah. So we have basic information available. That's, by the way, one of the reasons why we use this platform. We have basic information to go much faster. Right? So the whole problem of making an HD map is people believe, just as they believed in the old days, that making a navigable map was unaffordable. Now people believe HD maps, which is very detailed, very accurate, is unaffordable. It's not unaffordable. You need to be clever about it, and you need to use AI and AI platforms to automatically create and maintain, because that's an even bigger problem.
Because the world's changing.
Absolutely.
The world's changing. So you collect differences in the map.
Second.
We send it up to your cloud.
Yeah.
You've got to find a way to filter out all the junk, figure out what the major differences are, and fuse it with the new map. Isn't that right?
And we get images in, we get traces in. Just to give you an idea, I think we get over 7 billion traces in a day. That's a lot of information. And that's why we need platforms like that. So that's also the same with localization. If you want to localize your car with a centimeter accuracy, you don't want to miss 20 centimeters when you have a self-driving car. Then you need that information, which we have as road DNA, and that does the localization, also on your platform.
And so between the two of us, we are going to endeavor to map 47 million known civilization roads that are drivable.
Let's make that 60, then we have the whole
60 million miles. We are 100,000 miles into it.
120. Hey, that's 20% more, right?
And so,
and tomorrow even more.
And so what we need to do, of course, it sounds like a lot, but the fact is this. Once we get going, and we need a computing platform that can process at super real time. We need to process at super real time. And so what that means is if we collected a video for a day, we need to process that video in an hour. And so once we can do that and fuse it into an HD map, we'll get through 60 million miles in a hurry.
I go even a step further.
You're going to go to Mars?
That would be, no, that's another guy. But if we put that in mobile mapping fans, we can think about putting it in all kinds of commercial vehicles. We can think about putting it in cars, then actually maintain the HD map in the car itself. That's kind of the holy grail.
That's right. Incredible. Well, the future of autonomous vehicles, the future of self-driving cars, requires a very high-quality HD map. We're all counting on you.
We're going to build it.
Thank you.
Thanks, Jensen.
Congratulations. Thank you. Okay, let me show you something new. Thank you, Alain. Every time I hear Alain Duté's name, I actually think of Alain Ducasse as well. Alain Duté and Alain Ducasse. Are there only engineers in the audience? There are nobody in the audience who enjoys food? Yeah, that's right, Alain Ducasse. Okay. Thank you, sorry about that. This is 15,000 watts that I'm standing in front of. You know, I'm getting a tan in the back of my back. Okay, so I want to show you guys something new. You guys know that in order to create a self-driving car, there's the computing platform has to process information fast enough, and the sensor information is coming in from all over. You've got, of course, the simple stuff like GPS and the IMU and the rotation of your tires and your steering wheel. You also have the cameras that are coming in all around you. You have LiDARs, you have radars, and then now, as you heard from Alain, we also have HD map. All of this information is fused together as the input information into your car's operating system. And this information is being changed and updated and ingested in real time. This is the ultimate real-time, high-throughput supercomputing problem. And you've got to get that job done. You've got to get that job done. Best effort is not enough. It is not enough that when you hit enter, it says, you know, I tried. I just wasn't able to detect it in time. Next time, when the car is not traveling so fast, I will be able to detect it in time. It has to be high throughput. It's got to be mission critical. The algorithm for basically driving self-driving cars, the basic functionality I described, there's sensing, there's localization, there's planning, and there's the action taking. What I want to show you today is this. This is our operating system. The operating system is much, much more than this, but I want to show you the algorithms part of the operating system, and I want to show you an update of where we are. Basically, the way it works is this. The sensor information is coming in on the left. We have 3 artificial intelligence networks running on this car. 3 deep learning algorithms. The first one is just detecting things. We detect cars, we detect lanes, we detect signs, we detect cones, we detect things. We detect things, okay? It's called DriveNet, we detect things. As it turns out, none of us drives like that. None of us drive by going, no cow, no dog, no person, no car, no cone, no tree, no lake, no house, no truck, the list could be pretty long. It would be a debilitating way to drive. We detect these things for 2 reasons. One, we want to continuously update our HD map in the cloud. And there are several different markers that we see that can help us figure out where we are. Number 2, as a backup, just in case, as a backup. But the real way of driving is this. You detect what's safe to drive. When you're driving, you're detecting, look at that, it's a road, it's safe, look, it's open. There's nothing inside. The absence of things is open road. There's a network that is doing segmentation and figuring out where is it safe to drive. Not what not to hit, but where is it safe to drive. However, it turns out there's even a third network, and really the way that we drive. When we're driving, we're not thinking at all, unfortunately. When we're driving, it's just a behavior like playing tennis. It's a behavior. You simply grab the steering wheel, you start driving. All of the sensory information comes in, your brain is thinking, it's working, and it's doing completely by reflex, and we just drive. And that's one of the reasons why we can listen to a book while we drive. That's one of the reasons why we can have a conversation while we drive. When we're driving, it is a behavior. We have a third neural network called PilotNet, and it's simply a behavior network, okay? Not a detection network, a behavior network. So the first thing is this. The first section is we detect everything around our car. We create one of the most important data structures of self-driving cars called the occupancy grid. The occupancy grid is a 3-dimensional grid that's being updated completely in real time with all of the sensor information, all the detection networks, and it's creating this 3-dimensional mesh of your world. It's creating a virtual world. This is the virtual mathematical world based on all of the sensor information that it has accumulated. It's called the occupancy grid. That occupancy grid is, if you will, the primary asset, the database of the self-driving car. That occupancy grid then is tested against what the car would like to do. The car is driving by itself using PilotNet. It's going to go and start driving based on just what it sees. We're going to tell it, go in that direction, it's going to go. It's going to start driving based on everything that we taught it. And it's going to be tested against the future prediction of everything around the car. And if we were to hit something or the path would lead to a collision, in the near future, we would, of course, override it. Okay? So, and then what we do is because we would like to test that our understanding of the world is consistent with the understanding of the car. That our understanding of what we see is consistent with the understanding of the car. We visualize the occupancy grid in a virtual reality, if you will, computer graphics of what the car sees, the artificial intelligence car sees. And so let me first show you the upper left-hand corner just detecting things. Justin, please. This is in California. We're detecting things. Now, when we detect, this is our latest net. We're going to detect three-dimensional objects, because a car, as you know, is not a flat image. So we have to detect what we think is the volume around the car. Okay, and all of that information now gets included into our occupancy grid. We would also like to know where the lanes are. Okay, we'd like to know where the lanes are. We would also, those are our easy things. We would also like to know where is it safe to drive. Now this is really cool. Look at this. It's looking at the scene and it's saying, you know what? You see the yellow? All the yellows, the red, passenger, not safe. Yellow, not safe. Red, not safe. Blue, safe. You see this? Okay. Red, it recognizes it recognizes pedestrians. Not safe. Please do not go there. Does that make sense? You see that? Red is pedestrians, yellow are cars. Okay? And it's simply looking at every single image and saying, where is it okay to drive? Where is it okay to drive? I don't necessarily drive there, but where is it okay to drive? First of all, where is it okay to drive? And when I'm, of course, driving, this is what I would see. Now, of course, I would never go into the other lane because I know the rules of the road. But otherwise, I can pretty much drive in the areas that is safe to drive. Now, let's put it all together, Justin. And so we got detecting the cars, detecting the lanes. It's running on the Drive PX computer, the operating system called DriveWorks, and it's detecting these things, okay? Now, these things are all getting put into the occupancy grid, as I mentioned earlier. Let's go back to the slides, please. Okay, so you saw all these network detections. We take what I'm going to show you now is the occupancy grid. However, before you can have the occupancy grid, you have to have the HD map, in this case from TomTom, and it tells us where the lanes are, it tells us where the signs are, and based on our ego motion, which is the motion of the car, we figure out where we are on the road. It's called localization, okay? It's a very simple version of reasoning. The car's reasoning about where am I in the world? And so let's show people what the car sees. Okay, so this is our digital dashboard. This comes off of Drive PX2. As you know, one of the things that we do very well is computer graphics. I've had people look at this and they go, wow, it's amazing, the graphics you guys can do. And I said, I know, thank you. We learned it recently. It turns out that the computer graphics you're seeing here is actually quite remarkable. This team of young engineers over here, Justin, why don't you, come on, you guys, stand up, take a bow. I know you haven't slept. Thanks, guys. It's amazing what you could do on caffeine alone. It is, you know, whereas deep learning is the fuel of artificial intelligence, caffeine is the fuel of deep learning engineers. And so what you're looking at, this is the occupancy grid. This is the mind of the computer. This is literally the data structure of the computer. Okay? This is the data structure of the computer. And so figured out where it is in the lane. These are the cars next to it. Can you guys see this? And we're detecting the cars and tracking the cars in 360. Justin, does it make sense to show the front video? Did you want to do that?
Sure. Yeah, the video, or we can also enter into sort of a auto cruise mode where the car's driving itself like that.
Okay, so when we're in auto cruise mode, the digital dash changes pretty dramatically to let us know that it is in auto cruise mode.
Yeah, it's got to be a big change.
Yeah.
Yeah, absolutely.
And so now these are all the cars that we detect. Notice the cars in front of us, we're detecting these cars. Okay? So you see the cars. And so what's happening here is we're detecting, we're localizing, connecting to the HD map. We create an occupancy grid, and this is the visualization of the occupancy grid. When you look out the window and it's inconsistent with this, then you know that something is wrong. I would go back to manual mode. File a bug with NVIDIA, okay? And we'll get on it right away.
Yeah, and it's so much more sophisticated and difficult to represent this full 3D space rather than just some bounding boxes. So this really represents really advanced deep learning to be able to identify the exact locations of all of these.
Right.
Yeah.
And
To
so
really
what
build
Justin's
a
saying
true
is by
occupancy
recognizing the bounding boxes, we know the extent
That's right.
of that car in the occupancy grid. It could be a little tiny Mini Cooper. It could be a super, super long truck,
That's right.
right? Okay, so visualization of the occupancy grid. Now let's come back to the slides, please. All right, so what you saw earlier is detection, and then you saw us, you didn't see the occupancy grid, but you saw the visualization of the occupancy grid, which is in this UX, which I think is going to be pretty important to the future of self-driving cars, actually. You want the driver, you want the passengers to know that the car has the situation in hand, and you want to be able to calibrate against where it wants to drive and where you think it ought to drive. Now I want to talk to you about PilotNet. The fact of the matter is, when we're driving, we don't do any Newtonian physics. When we're driving, we're not doing any calculus. When we're driving, we just drive. And so the question is, how do we get a car to just drive? And what we're going to show you is this. This is BB-8. This is the latest version of our network, and we've been teaching it how to drive. Now remember this. BB-8 has no detection networks inside. When BB-8 is driving, it's doing, we didn't tell it, detect a cone, detect a lane, detect a post, detect a fence, detect cars, detect the absence of roads. We didn't tell BB-8 anything. We just drove. We drove and drove and drove and drove and drove and drove, and BB-8 imitating us. So what BB-8 is going to do is imitate us. So the question is this: when we're driving, what do we see, and why did we do it? It turns out we don't have to describe it using algorithms. We don't have to describe it using equations. We only have to do it over and over and over again until BB-8 generalizes, it detected the features, and it generalizes what is driving behavior. Ladies and gentlemen, BB-8.
Oh yeah, good. The universal sign for auto.
There are no lanes here, ladies and gentlemen. That's barely a road. That is incredibly strange that the car did that.
I'm not touching anything. So cool. And the auto?
No math. Just imitation. And then learn how to drive in the dark.
Got it.
What do you guys think? Autonomous machines. The thing that's really cool is this. I want to show you what's in BB-8's mind. Is that okay? The question is, what did it see? The question is, what did it see? And so we just started driving, and eventually it learned how to drive just like us. Okay? It learned how to drive like us. The question is, what did it see? What are the things that it saw that it learned and generalized and eventually say, these things matter to driving? These things matter to driving. I think you'll be kind of surprised. Those sparkles are BB-8's AI neurons. That's what's firing on this video. And look, it's kind of interesting. It's looking at that corner because that particular car is kind of closer to us. And every now and then, it checks the car in front. And it checks the car to the right. Every now and then. It's always looking at the lanes, making sure I'm staying inside it. Everything else that's not lit, wherever there's no sparkles, non-information to BB-8. These are the things that it figured out that were important to its driving behavior. And then as a result, it just stayed in the middle of the lane all by itself, did no calculations, because it knew that largely when we drove, we stayed in the middle of the lanes. It knew that when we drove, when there are no lanes, we stayed in the middle of the road. And it recognized how to discern a mud road, a dirt road in the dark next to bushes. That we don't seem to drive over bushes. We seem to drive over the dirt road. Okay, ladies and gentlemen, BB-8. So today we're announcing that DriveWorks that we talked about in the beginning of the year has made enormous progress, and we're in the process of packaging all that up. Our strategy with DriveWorks is this. DrivePX and DriveWorks is an open platform. It's an open platform. It's an open platform that Tier 1 OEMs and Tier 1 ODMs and Tier 1 OEMs and car companies have the ability to pick off the pieces that they would like to use or the pieces they would like to replace. And together, we will work together as an industry to move autonomous driving forward. DriveWorks is an open platform. We have reached Alpha 1. As you know, that this is going to be an area of research and development for years to come. And even though we're going to see some self-driving cars get on the road here in the next year, or no more than next year and no more than the next couple of years, we're going to continue to enhance the software. Today, we're announcing that DriveWorks Alpha 1 will be released to our early partners in October. After that, of which they could use pieces that they like, pieces that they would like to replace, and after that, we will update it every 2 months. Just as we continue to learn as humans, our car will continue to learn, and the network will get better and better and better. Considering what we've achieved in just 1 year's time, imagine where we would be in another couple, 2-3 years. DriveWorks Alpha 1. Well, the number of autonomous vehicles on the road are increasing, and we're working with some 80 companies, 80 partners around the world, one after another over the next several months, the coming year, are going to be revealed. I think that the vision of having an AI computing platform, by which cars could be built on top of, that has the ability to do perception and sensing, localization and reasoning, planning and driving. The ability to have all of that on top of a deep learning platform is really quite the right answer at this point. And we're seeing just really, really rapid developments across all of our partners. Well, the work that you've seen so far is really at this intersection. You know, whether it's the company slide that I showed you, or all of the different examples that I've created, that I've shown you so far, they share one thing in common. That the work that we are doing, that NVIDIA is doing, is at this intersection between visual computing, which in our brain consumes the vast majority of our neural cortex, AI, and high-performance computing. The work that we do have to be achieved very, very quickly. This area of computing, AI, we call AI computing, would enable the future of intelligent machines. And we're super excited about this area. So much so that several years ago we decided that the world needs a processor that is designed specifically for this intersection. We started working on a project internally called Project Xavier. And ladies, today, I'm announcing Project Xavier to you. Project Xavier is basically an AI supercomputer SoC. 7 billion transistors. The reason we put 7 billion transistors into context for you. 7 billion transistors is equivalent to the largest CPU the world's ever made. The highest performance server CPU, the largest number of cores you can find, is just about 7 billion transistors. This is the largest processor endeavor that I know of that we have ever done. Not only is it large, it is also multifunctional. Not only is it multifunctional, the throughput requirement necessary is just really quite tremendous. The ability to support HD cameras all over you, LiDARs and radars, the ability to do three fundamental things. Deep learning, computer vision, and high-performance computing. These three fundamental elements of computing we think is going to be super, super exciting area for us to innovate. And we've taken an enormous chance to create Xavier, and I'm just so incredibly excited about it. 7 billion transistors, 8 high-performance CPU cores inside, 512 of our next generation GPU cores, has a brand new computer vision accelerator, moving video processing to 8K, process it in full HDR. And the reason for that, in the case of autonomous driving, we need a very, very precise black box inside the car, and it should be recording things all the time and recording it in HDR. And it's designed for ASIL C functional safety. This is the greatest SoC endeavor I have ever known, and we have been building chips for a very long time. And so this is Project Xavier, our next generation SoC. We'll have samples end of next year. Well, let me tell you what it looks like when you have Xavier. This is Drive PX2. The Drive PX2 motherboard includes 2 latest generation Tegra SoCs and 2 discrete GPUs. Okay? The Drive PX2 in its full configuration is 2 Parkers and 2 Pascal GPUs. It performs 20 trillion operations per second. 20 trillion operations per second of deep learning capability. And it has 120 spec ins, all in about 80 watts. Okay? So this configuration, 120 tops and 20 tops and 120 spec ins is 80 watts. Well, that's approximately equal to 150 MacBooks, 150 MacBook Pros, all in a little tiny computer that sits inside the car. Well, Xavier is exactly the same architecture. It's 20 tops, it's 160 spec ins, and it's 20 watts. And a little tiny board like this, okay? Xavier. And so just imagine what an autonomous vehicle could do in the near future with Xavier. So, super excited about Xavier. We have plenty of time before next year, and I'll give you more details as we go. Let me quickly summarize our announcements today. We have introduced an end-to-end deep learning platform. I introduced the new P40 and P4 today. It opens up a brand new market for GPU deep learning. We have great partners for enterprise, IBM, and now really excited to announce SAP. We now have the ability to take GPU deep learning from training all the way to inferencing in data centers, from training the network to applying the networks to queries, the incredible number of queries that consumer applications have, from training the networks to actually finding insight for your business. Okay? So first thing is announcement of P40 and P4. The second set of announcements has to do with our self-driving car initiative. We are today announcing that DriveWorks Alpha 1 all of the capabilities that we talked about will be released to our partners, first release in October, and then after that, every 2 months. We announced a partnership with TomTom that together we will enable a autonomous driving platform from cloud to car. And then lastly, the future of AI computing, this processor we called Xavier, one of the greatest endeavors of our company. Well, I think you can get a sense now of why I think AI is going to be so important for the future of the computer industry and frankly, for the future of the world. There are so many ideas now of the applications of AI, new problems that we're able to solve that we weren't able to solve before. Whether it's AI for transportation, a $10 trillion industry that we have an opportunity to make a big difference in. AI to revolutionize medicine, and then AI, of course, to completely, utterly revolutionize society with intelligent machines that are among us, helping us do things that are mundane, helping us do things that are dangerous, or even helping us do things that we simply have no possibility of doing ourselves. This is a great new era of computing. I want to welcome all of you to GTC, and I look forward to seeing all of you today.